Section 10.2 is on finding arc measures. The math is not hard. We just have some new vocabulary to get down. So the first thing we want to talk about is what we call a central angle. So when we take a circle and we drop a radius to the edge, and we have a second radius to another edge of the circle, or another side of the circle, the outside of the circle, we have something called a central angle. That central angle is an angle whose vertex is the center of a circle. Makes sense, right? So we define a central angle as an angle whose vertex is the center of the circle. Okay? Not yet. Okay? So an angle whose vertex is the center of the circle is a central angle, and it creates something called a minor arc. So when you think of minor league baseball versus major league baseball, what's the difference? The level of talent, the amount of money that they make, right? Okay. A minor league team is smaller or has less talent or has less money to devote to their talent. A major league baseball team has a much bigger amount of money to devote to their talent. So a minor arc is an arc created by a central angle that is less than 180 degrees. A minor arc is an arc whose central angle is less than 180 degrees. Okay. What do you think a major arc is then? Yes, an arc whose central angle is more than 180 degrees. So there's our major arc. Now, to be able to name them, we have to have some kind of a naming scheme. And we have a new symbol for you. The symbol is one that I wasn't able to find in PowerPoint last night when I was working on this at 11 o'clock at night, because I don't have the math type font or the math type program with it. But if I want to name this arc that goes from B to C, the red arc on my smartboard, I call that arc BC, and I put an arc over the top. So it's not a segment mark, it's an actual arc on top. That's a minor arc. When I want to name my major arc, I have to use a 3-letter combination. So the major arc is one that is corresponding to this large central angle. So CDB is the name of the major arc. 3-letter combination for a major arc, 2-letter combination for a minor arc. And of course, I could call that DBDC as well. So a major arc is named with a 2-letter combination. A minor arc is named with a 2-letter combination. A major arc is named with a 3-letter combination. So the bigger arc is the one that is more than 180 degrees. I'll grab a different color pen here. Its central angle is more than 180 degrees, so it's the rest of the circle. So on your paper, you can color your minor arc with one color and kind of highlight or trace over that portion of the circle, and then use a different color to color in your major arc and trace that around. Okay. Have a seat, please. Okay. Then what do you think happens if we have an arc that has exactly 180 degree central angle? What are we going to call that? A semicircle. So here is an arc with exactly 180 degrees for its central angle, and we call it a semicircle, because a semicircle is an arc whose endpoints are the endpoints of a diameter. The endpoints of a semicircle's arc are the endpoints of a diameter. All right. A couple more seconds. And if I wanted to name my lower semicircle, I could name this arc CDB, three-letter combination. If I want to name the upper one, I would need to add another letter, another point, and call it CEB. Okay. So what questions do you have on this slide? Okay, a semicircle would be CDB because it starts at a diameter's endpoint and ends at a diameter's endpoint, and it goes through point D. Yep. Then if we wanted to talk about the upper semicircle, we could call it CEB because it starts at a diameter's endpoint, goes through a point on that circle, and then that semicircle, and then ends at the diameter's endpoint. Absolutely. So central angles form major arcs and minor arcs. A minor arc is denoted with a two-letter combination. A major arc is denoted with a three-letter combination. A minor arc has an intercepted angle or a central angle that is less than 180 degrees. A major arc is more than 180 degrees. All right, we ready for the next slide? Okay, so next slide says that when we measure arcs, our book is going to ask us to find the measure of arc AB. Notice the letter M in front. And they said that since central angle ACB is 50 degrees, then that arc has a measure of 50 degrees. The arc created by the central angle has the same measure as the central angle itself. That part I think is pretty much on your. You'll want to write the measure of a minor arc equals the measure of its central angle, and you can abbreviate, save some pencil lead. I'll ask for your assignment after we're done with this new material. I'll go over any questions that you have. Okay. So they told us that this minor arc has a central angle of 50 degrees, so its measure is 50 degrees. We have a major arc that has a central angle that starts at the radius CA and ends at the radius CB. Okay, because this is a major arc, and we want to know what its angle. So the red is the distance between, this is this angle, whereas the blue was this angle. So how many degrees are there in a whole circle? 360. So if a minor arc has a measure of 50 degrees and the major arc is the rest of the circle, how much is it? 310. Okay. So the measure of arc ADB is 310 degrees. So the whole circle is 360. We have 50 degrees for the minor arc. That leaves us with 310 degrees for the major arc. Okay. So the math is not hard, just a lot of new vocabulary, new symbolism. Okay. Okay. Save some paper, sure. Okay. All right. So now We have circle C. Remember this symbol we introduced yesterday? That's the circle symbol, a circle with a dot in the middle, a center in the middle. Circle C has AB as its diameter. So AB goes through the center. It's a chord that goes through the center. And we want to know what is the measure of each of these arcs. So the measure of arc AD. The measure of an arc is equal to the measure of its central angle, right? So how big is the central angle? How will we find that? 180 minus 70. And we get 110 degrees. Okay, so that's the measure of arc AD. Okay, now they want us to tell what the measure of DAB is. Okay, so now we're going from D to A to B. So D to A to B. Okay, so what do you think? How are we going to find that? Good. 360 minus 70, because we have a whole circle less that minor arc. 290 degrees. What's wrong, Maddie? Measure of BDA. Okay, now we want the measure of BDA. B to D to A. 180. Why? It's a 100 semicircle, or 110 plus 70, right? Axton, don't throw things. Okay. So we're used to seeing pie charts, right? Sorry. Go back. Okay. Because a whole circle is 360, right? And a semicircle is 180. So when we look at the measure of BDA, B to D to A has this half circle as its central angle. So half of a circle is 180. A whole circle is 360. Okay. Mm-hmm. Yep. The central angle has the same, the arc measure is the same as the central angle. Yep. So far, so good? Okay. So next, we have pie charts, and we're used to seeing these with things like 25% of the population does this, that, or the other thing, right? What is 25% of a whole circle? A quarter, which would be how many degrees? And a whole circle is 360, so a quarter, a fourth of it would be 90, right? So we have the frequency of internet use in the US as information, or as data. So Statistica gave us this information, and I changed it to a chart with angle measures in it. So when we look at this, we can see that a fourth of the people, 90 degrees of this pie, of this circle, uses the internet all day long. Okay. Most likely people that work in offices. Okay. Of course they sleep, but this is talking about their waking hours. Okay. And every hour, 26% of the people, which represents 94 degrees on our circle, use the internet every hour. Okay. Once a day or less was 25 degrees, and 2 to 4 times a day is 151 degrees. So your book can ask you, as in your assignment, to tell me what is the measure of arc BDA. BDA. And what they're asking for is how many degrees does the central angle that makes arc BDA have? So how many degrees is that? 184. 90 plus 94. Okay. Or we can ask you, okay, well, who only uses it once a day or less? What is the measure of arc DE? Okay. And so when we say DE, we're looking for a minor arc, aren't we? Okay. So from D to E, that includes B. So it would be 115. Why is it 115? Exactly. We take our 90 degrees from D to B and add on our 25 from B to E. We added 90 plus 25. Okay, because we want to go from D to E, so we have to combine the 90 with the 25. Okay, to get BDA, we started at B and went to D and then to A. So it would be from, yep, 90 and 94. B to D to A. Yep. Okay. So it's not hard math. It's just new vocabulary, new symbolism, new terminology. The math itself isn't hard in this section. Okay? All right, so just mainly adding, exactly. I have 2 more things to talk about. So first of all, if you're curious, this was the US. This is the data that I took from Statistica to get that graph. And you can see that we had about 25% that are on all day long. Which country has 51% on all day long? That's Brazil. Okay. So Brazil has a very large population, at least in this sample of the people that they interviewed, who are on the internet constantly. And then if you look at China, only about 15% are on it all the time, and 13% of Japan. I'm not sure. China, yeah, there's a lot of censorship on the internet. Okay. Okay, so 2 more concepts. One of them is whether or not circles are congruent. So if you remember, back when we talked about triangles being congruent, we had to use hypotenuse leg, or side, 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 or side, angle, side, or angle, angle, side. We had about 5 different ways to prove triangles congruent. The great thing about circles, not a lot of edges, not a lot of angles, right? They only have 2 parts. They have a center and they have the exterior of the circle, don't they? So if 2 triangles are congruent, it's because they have equal radii. When we have 2 circles with equal radii, those triangles are congruent. So everybody good with this one? Congruent circles have equal radii. Okay? So 2 arcs are going to be congruent if and only if they have the same measure and they are arcs of the same circle, or they have to be arcs of congruent circles. Okay? Two arcs will be congruent if they have equal measures and are arcs of either the same circle with central angles the same or congruent circles. No. One of them is circle B. Are arcs CD and EF congruent? Yes. Why? Their central angles are the same, right? And they're in the same circle, so they have to have the same radius, don't they? Okay. What do you think about arc in circle Q? Are arc RS and TU congruent? They share the same central angle. Are they in the same circle? No. Do those circles have the same radius? No. So this distance around this portion of this arc is going to be much smaller than the distance around this portion of this arc. So now we're talking arc lengths. How long is that arc? Okay, so this is a no. Circles aren't congruent. Okay. Last example of this one, what do you think? Are they congruent? Not the same circle, right? Do they have the same central angle? Yes. Do they have the same radius? Yes. How do you know? 95 degrees and the tick mark. So these are a yes. The circles are congruent. They have the same central angle. That means the distance from U to V will be the same as the distance from V to, or Y to Z. Okay, so when we want to know the measure of the angle, we ask for the measure of arc UV. If we want to know how long this red area is, we'll just ask you for the distance between U and V. And we'll talk about that more tomorrow. Monday. Sorry. Okay, next time we meet. Okay, one last point. This is going to seem logical. Because there are no edges, no angles, and so forth in a circle, all circles are going to be similar. Circles are congruent if they have the same radius, but all the circles are going to be similar. Okay? As the radius gets larger or smaller, they'll be similar. They'll be proportional. Okay? One quick demonstration of that. I have a GeoGebra worksheet to show you. These are our arc lengths in degrees. So as you can see, I have a circle with radius of 5. And I have a central angle that's 50.48 degrees. The arc's length, or the measure of the arc, is 50.48, but the arc's length is 4.41. As I move this point, the central angle matches the arc's measure, but notice that the length of the arc is changing. It's getting larger. I work my way around here, and now I'm over 180 degrees, right? So it's a major arc. I come back, and it'll be back to a minor arc. I can also shrink it by moving the radius in, and now I can move things around as well. And as I approach that semicircle mark, I hit pi. Maybe, if the smartboard lets me. Okay? All right, so you have your assignment. try to get it done in class, and I'll answer any questions you have over section 10.1.